Hello students, my name is Shashank Shekhar. So we have started the D block element. So today we will first of all do a revision of what we have learned till now. Then we will move to interstitial compound and then we will move to alloy and see the difference between these two, right? So let us start our class. So first of all, we have studied about the position of the D block elements, right? So we have studied that it is flanked between the S and P block, and it is a kind of transition. It is a kind of transitory phase, right? So we are moving from S block to P block. So that is the reason they are called as transition element. So that specifies the position of the transition element. So let me make one thing clear that okay, all the elements that are present between the S block and the P block elements are called as transition elements, right? But the case is that the exception is that the D block elements are those which have partially filled orbitals in their atomic or ionic state. So that's the statement that distinguishes some of the compound, some of the element, right? So what does it say is that if you are saying that, right, we have a D block element, then it must have an empty d orbital. So that empty d orbital case can either be in the atomic state or in the ionic state. Either of them are good with you. Okay. Now, as we know that there is a specific pattern for each of the elements. I mean, say we have S block element or either we have P block element. They have a specific pattern. So similar to that, now here is the general pattern of filling the d block elements electrons, right? So first of all, it is n minus 1d, which can have 1 to 10 electrons, then ns 1 to 2 electrons, right? So suppose we are saying that, okay, we are in the 6s, then the d orbital, corresponding d orbital will be 5d, okay? And this other number of electrons, okay, we know it very well that d orbital, d subshell can accumulate 10 electrons. Similarly, s subshell can accumulate 2 electrons. Now here, n minus 1d represents the partially filled d orbital and ns represents the outermost s orbital. So we know it very well. So since it is ns, so it will be the outermost and it is n minus 1. So it is the penultimate shell. Now, moving on to the electronic configuration of various elements. First, we have here of scandium, so which has an atomic number of 21. So its electronic configuration is, first of all, we will write the electronic configuration of argon, which is a noble gas. Then we have 3d1 4s2. Okay. Next, we have iron, which is 3d6 4s2. Next, we have copper, which is 3d10 4s1. Right. So here, one thing you have to notice is that, so if you just follow the n plus l rule, then it says that here 4s should be filled completely, and then it should be 3d9. So I want to say here that it should be 4s2 3d9 rather than 3d10 4s1. But why it is so? Because so that we can have a half filled d orbital. So sorry, full filled d orbital. So for that reason, we have done this thing. Next is, we have seen what is ionization energy and how does this changes in the periodic table for the d block element. So let us get a quick revision of it. So first of all, ionization itself is basically the energy which is required to remove an electron from a gaseous atom or ion. So this is very important line here, that the atom from which we are removing the electron, that must be in the gaseous phase, and that thing is this energy is measured in kilojoule per mole. Generally this unit is used rather than joule per mole, so that the complication of digits can be made easier. Okay. Now, talking about the general trend, we know that as we move across the first row transition element from left to right, the ionization enthalpy increases. So that thing is very obvious, because when we move from left to right, what we are doing is we are increasing the number of electrons on the outermost shell, and that increases the electrostatic force of attraction on the shell and hence bring it closer to the nucleus. Now, it becomes difficult as we move from left to right to remove the electron. Second, this increase in ionization enthalpy is due to the increased effective nuclear charge. Okay, so that same thing is mentioned here. That why is it so? Because as the number of electrons increases in the shell, outermost shell, then the effective nuclear charge that is experienced by the electron also increases, right? The increased nuclear charge attracts the electron more strongly, making it more difficult to remove. So this thing is the common trend. Okay, this is the common trend that we see, and this is seen quite in a good manner for the first transition element. But for the second and third, there are some you can say particularities. We will see to it. Now, talking about exceptions, again, we have exceptions here. So while the general trend is ionization enthalpy holds for most of the first two elements, we have said that, but there are exceptions. First of all, the exception is between chromium and copper. Now, these elements, if you see the electronic configuration, they have half filled and full filled. So chromium is half filled and copper is full filled d orbital, which provides them extra stability. So for that reason, the removal of electron from these atoms requires more energy. Okay, this requires more energy, leading to a higher ionization energy compared to the neighboring elements. Means on the left hand side and the right hand side, the element the increase is quite high. Okay, so what I'm saying is that as compared to the elements that are next to the left hand side and right hand side, they have a greater ionization enthalpy. Clear? Okay. So this is for chromium and copper. So we have seen the electronic configuration of copper just now. It is 3d10-4s1. So it has a completely filled d orbital, and that is the reason it has a higher, say, ionization enthalpy. Clear? Okay. Now next. So next is chromium and copper. Sorry, manganese. Okay. So manganese also show a higher ionization enthalpy due to the d5 atomic orbital. Okay, it is the d5 orbital, right? Because it is half filled. Okay, this is d5 configuration, so it is half filled, right? So due to due to the half filled configuration, it has a higher ionization enthalpy because of the extra stability that it gets due to d5 configuration. Clear? Okay. Next, we will move to oxidation state. So as compared to the S and P block element, the transition metals show a variety of oxidation state because of the involvement of d orbital. We know it. This thing is seen. Okay, so we have seen that can show an oxidation state of +7, +2, +3, right? But the most common common oxidation state is of course +2 and +3. But we can see +7, +5, right? So we can see those electronic configuration also. Now, as I've said that this is due to the availability of d orbital that makes it possible for the transition element to show this variety of the oxidation state. Next is okay, we have said that okay, they can show +4, +5, and +6. So we'll see some examples of it. So for example, there is a +7 oxidation state that is observed in case of manganese. Due to this reason, it can form compounds like permanganate, that is KMnO4. Now, the higher oxidation states are observed when the transition element form covalent compound with highly electronegative elements such as oxygen and fluorine, right? So it is said that this higher oxidation state is possible if the transition element is forming covalent compound, especially with the oxygen and fluorine. Now, the oxidation state of its transition element is also responsible for the it's also dependent upon the nature of the ligand in coordination compound. So when we move to the next chapter, we will see the coordination compound, and there we will see that it is capable of, say, chelating with this, or not chelating, I would say coordinating with this ligand, and this oxidation state is also responsible for this coordination. Okay. Now let us talk about the trends in oxidation state. So we have said that okay, we have a variety of oxidation state. It can show +2, +3, which is the most common one. In addition to that, it can show from +4 to +7, right? So, but still there is a trend for it. So as we move from left to right, we will see that the number of oxidation states that is possible for an element, it increases first of all, then it goes to a maximum, then after a certain time it decreases. Okay, means after a certain element it starts to decrease. Clear? Now what is the reason behind it? Why do we see this kind of trend? So first of all, the less number of oxidation state on the left hand side is due to the less number of electrons. So it is as simple as that. So since we are moving from left to right, the number of electrons is less on the left hand side. Therefore, the number of possible oxidation state is also less for the elements that are present on the left hand side. Now, as the number of electrons increases, the number of oxidation state possible for that element also increases. Clear? But after a certain time, what happens is that the effective nuclear charge is increasing. We know that we have already seen the ionization enthalpy, which is a result of the increased effective nuclear charge. So as the effective nuclear charge increases, so after some time, what we see is that that the maximum number of oxidation state goes to the middle and starts to decrease after a certain element. Okay, we will see that trend also. Now, as a result, it becomes more difficult for the transition element to lose electron. Of course, it is due to the higher effective nuclear charge. Now, the maximum oxidation state is usually reached in the middle of the period. I've said that is for around group 7 or group 8 elements. Now, there are some exceptions to the general trend of increasing oxidation state across a period. For example, we have the exception of copper that exhibit a maximum oxidation state of +2 despite being in the middle of the period. Okay, so we have seen this thing that in case of copper, although it is present in the middle, it does not show a maximum oxidation state. Okay, no, it does not show a number of oxidation state. It can show only +2 oxidation state. And why is it so? Of course, it is due to the D10 configuration in its +2 oxidation state. Clear? Similarly, the elements chromium exhibit a maximum oxidation state of +6, even though it is in the middle of the period, right? Even though it is in the middle of the period, it can show what it can show. It can show a maximum oxidation state of +6. Now, this is due to the D5 configuration in the +6 oxidation state, which is also stable. So we know that it can go up to +7, but it does not did so. It is not seen. Why? Because it has a D5 configuration in its +6 oxidation states. Clear? Okay. Now next, as we move from left to right, now we'll talk about the atomic radii. Right? We will talk about the atomic radii. So as we move across a period, we have seen that due to the increased effective nuclear charge, the outermost shell shrinks towards the nucleus, and due to that reason, this size of the atomic radii of the outermost shell decreases. Clear? Now, comparative to the first row transition element have uniform atomic radii compared to the main group. What is being said is that, so if you see the main group element, the trend in the main group element, then the decrease in the atomic radii, the rate of decrease in the atomic radii is quite high as compared to the D block element. Okay, why is it so? It is due to the D block element. In case of D block element, we can see that the atomic radii is varying. Of course, it is decreasing, but the variation in decrease is not that much. Now, this is because the additional electron are being added to the same principal quantum number, that is n is equals to 3. Similarly, similar subshell, that is d orbital. So the reason behind it is that, so because the electron that we are adding, it is going to the same subshell, that is n is equals to 3. It is not in the case of S and P block. The cell changes, of course, not the cell, of course, the subcell changes. But in case of d orbital, it is not so seen. Okay, because d orbital can accumulate a large number of electrons, that is 10. Now, there is also an influence of the electronic configuration. That is our half filled or full filled, which is seen in case of chromium and copper. So they have a higher atomic radii due to the repulsion between the electrons in the same subshell. Now, talking about the exception, so we know that there is a general decrease in the atomic radii, but in case of manganese and iron, they are larger than the chromium. Okay, why they are larger than the chromium? It is due to the presence of additional electron in the 3D subshell. Clear? Now, we have done a revision of what we have learned till now. Now we will move towards the interstitial compound. Okay, what are the interstitial compound and alloys? Although we have seen a small part of it in the previous lecture, now we will try to discuss it in more detail. So first of all, what is interstitial compound and how our interstitial compound is formed? So basically, the reason behind it is that, so first of all, you must remember that the D block elements, the atomic radii of D block elements is exceptionally high than our normal S and P block, like the nitrogen or hydrogen or carbon and any of those small elements. And if it is so, then there is a chance that between the D block element atoms, the interstitial atoms like your nitrogen, which is smaller in size, they can go through and get inserted in between, right? And as soon as we get it gets inserted in between, the results in the formation of interstitial compound. So how you can imagine it? So just take a bucket of rocks. Okay, so take bigger boulders of rock. Now you will see that there's gap between them, right? Now, if you put small pebbles in the between, you will see that they're able to accumulate that space. Now, what you do, you decrease the size of your say stone, or either you take sand, right? Now, if you take sand instead of your stone, then if you put small stones in between without any force, okay, without any force, then you will see that it will not go inside because there's no space in between, right? Because they're small in size. So basically what I want to make clear is here is that due to the large size of the atoms of the d block element, there exist an interstitial sites in the between. Okay, there's a space, vacant space, and in that vacant space, small atoms like nitrogen, hydrogen, and carbon, they can get in between. Now, what is the outcome of this? So first of all, due to the filling of the small atom, these compounds are hard and rigid. Why is it so? Because it is having a greater density. Initially, that same area would have been having say 10 atoms. Now, since carbon and nitrogen are being inserted in between, then there must be 12 atoms or there must be 13 atoms, and the density will increase. Now, as the density will increase, we know that the density is directly proportional to hardness. So as the density increases, the hardness increases. Now, talking about the chemical properties are not altered that much. Physical properties are altered. They are very much altered. So first is your density is altered. Then they become hard and rigid as compared to the parent compound we have taken. But there is no change in the chemical properties. They are, of course, they would alter in some way, but that alteration is not significant, right? But the significance is in the physical properties like density, rigidity, hardness, malleability, conductivity, and ductility. So, first of all, talking about density increases, rigidity increases, hardness increases. But metallic properties like malleability, conductivity, and ductility, they all decrease, right? They become brittle as compared to the parent compound. Okay, so if you just try to hammer them and convert them into sheet, then there is a chance that the crystal will break down. Now, steel and cast iron are the interstitial compound which are formed with carbon. So what we take iron and we just fill the interstitial side with carbon to get your steel and cast iron. Now, in the process of formation, the malleability and ductility are lost. So I have already mentioned it that the malleability and ductility goes down to a large extent, but the tenacity of the metal is increased. That is, toughness is increased. So transition element typically crystallize in either hexagonal close packing or face-centered cubic structure, which are both made up of layers of hexagonal close pack atoms. So both of these have a very similar lattice, have two types of interstices, right? So what is being said here that they either say get packed into hexagonal close packing or in the face-centered close packing, which are both are made up of layers of hexagonal close pack atoms. Now both of these have very similar lattice and have two type of interstices. Now first, each atom can have two tetrahedral holes, right? Implying a hole in between the four metal atoms. Second, each atom can have the octahedral hole. So these are the two type of interstices that can be seen. So what is being said here is that now I have said that the interstitial sites are being filled by the small elements, right? So what are the type of interstitial sites that can be made by with the help of this D block element arrangement? Okay, so those are first of all tetrahedral and the second is octahedral. So for each metal atom there are two tetrahedral atoms, and for each atom there are one octahedral hole, which is between the 6 atoms. So for tetrahedral it is between the 4 atoms, and for octahedral it is between the 6 atoms, and one atom can be inserted in between. So this is the pictorial representation of what I have said. So see, here what we have done is we have taken 4 atoms. Okay, so first we have placed 3 atoms in a triangular pattern. Then we have placed another atom on the top of it. Now in between there is a space, right? This is called a tetrahedral hole. Now what this carbon and nitrogen just can get in the between and can fill this interstitial site. Clear? Now what is the second possibility? The second possibility is that first of all we take again a triangular pattern. Now we take a inverted triangular pattern. Okay, with respect to this, it is inverted. This is pointing towards us and it is pointing away from us. Now if you place both of this on top of each other, you will get an octahedral hole, and of course this octahedral hole will be made from 6 atoms. See, 1, 2, 3, 4, 5, 6. Whereas the tetrahedral whole are made up of 4 atoms. That is 1, 2, 3, and top of it there is the fourth one. Now this is the octahedron that will be formed, and in the middle of it, the interstitial atoms like your carbon and hydrogen will get in between these. Similarly, this is the tetrahedron, and the carbon or your S block element, small element, will be inserted in between. Clear? So the transition metal have defects in their crystal lattice. This transition metal form interstitial compound as small atoms like carbon, hydrogen, and nitrogen are trapped inside the interstitial side in the crystal lattice of the metals. Now let us talk about the physical properties. We have seen a glimpse of it. Let us quantify all of those. So these compounds are very high melting point due to the greater density, because now since small holes are just filled up with the small elements as compared to the parent transition element. Next, they are of course hard in nature. Third is the conductivity exhibited by the compound is similar to the, means the conductivity is not affected by the interstitial site. Okay, so means due to the filling of interstitial site, the conductivity does not alter much. Now here very important thing is written that their hardness is increased up to an extent such that it is comparable to that of diamond. Okay, it is compared to that of diamond. The hardness of interstitial compound is used in alloy hardening and high-speed cutting tool tips hardening. Next is chemical properties. So what are the effects of chemical properties? Although the effect is not that much pronounced, so let us look what are the small chemical properties that are being affected. So these compounds are chemically inert in nature, of course, due to the extra stability that we're getting to the fulfillment of the interstitial compound. Now, Fe3C is an interstitial steel compound that governs many properties of steel. They are more reactive than the parent compound in general. Clear? So, as compared to the parent compound, they are more reactive. Although they are chemically inert, but in some cases they are more reactive, like in the case of, say, here the steel. So, Fe3S. So, what we have taken iron, and we have filled the interstitial holes with the help of carbon. Now let us talk about alloy. So we have talked about this interstitial compound. Now let us talk about the alloy. So in an alloy, the atoms of similar lattice try to accommodate with the atoms of another crystal lattice. So let us first of all let us just make me clear. Let me make clear one thing, that in case of interstitial compound, what we do is we insert small atoms in between. Clear? But in case of alloy, the lattice sites are say occupied by the either of the element, right? So in the previous case, the lattice sites are occupied by the parent one, and the holes are occupied by the say smaller atoms. But in this case, in case of alloy, what we see is that the lattice points are instead of hole, the lattice points are occupied both by the both elements, right? So the atoms of one element try to substitute the atoms of other element in the crystal lattice, as I said. Similarly, in the case of lanthanide is also same. So this is seen in the lanthanide also. Only those elements can form an alloy which have comparatively similar size in the atoms, and atoms of one element can substitute the atoms of another crystal lattice of a different lanthanide element. So what is being said here is that in case of interstitial compound, we have to take the small elements. Okay, we have to take the small elements to fill the interstitial hole. Okay, so the size should be comparatively small. But in case of alloy, the two elements which you are taking, or the three elements which you are taking, they all should have at least comparable size, so that once it is once it substitutes the lattice point of another, the crystal does not get distorted, or it does not shatter. It does not get shattered down. Right? Clear? Okay. So it this alloy are made up of lanthanides also. So different lanthanide elements are used because they have not much decrease or not much increase in their atomic size. So due to this reason, they are taken, and alloy is made up of this lanthanoid. Now, an important lanthanoid alloy is mesh metal. So it is an alloy of cerium, lanthanum, and other rare metal. So it is called as mesh metal. Now, talking about the uses of mesh metal, so they are used as flints for cigarette lighters. Okay, it is used for deoxidizer in vacuum tubes, and it is also used as an oxidizing agent in magnesium to contribute high strength and low resistance. Clear? Okay. Note, a mesh metal has a higher series of lanthanoid elements and has a variety of metallurgical applications also. Although the lanthanide cannot exist in free state, it is possible from them to exist in a combined state as in case of alloy. Now, what are the common uses of alloy? So, alloy steels are used for plates and pipes. Mesh metals, I have talked about mesh metals. It is basically lanthanoid metal 95%, iron 5%, and traces of sulfur, carbon, calcium, and aluminium. Next is magnesium-based alloy are used for making bullets, shells, lighter and flint. Okay, lighter flint. Mixed oxides as catalyst in petroleum cracking, and individual oxides as phosphorus in television screen and similar fluorescent surfaces. Now, this picture will make clear what is the difference between alloy and interstitial compound. See, so this is, so if I ask you which is the example of alloy and which is the sample of interstitial compound, so this is your alloy. Okay, this is your alloy and this is your interstitial compound. So in interstitial compound, what is being seen here is that these are the violet balls that are representing the parent atom elements. Okay, now in between we have small gaps. Now the small elements gets in between and this creates a lattice. Clear? Whereas in case of alloy, what we see is that we have taken two different elements. Now this both element have comparable atomic radii. Okay, they both have comparable atomic radii, and due to that reason, instead of getting in between, what they have done is they have substituted the purple atom with the yellow atom. So they have substituted one lattice point only. Okay. Similarly, here it is substituting one, here it is substituting one, and here it is substituting one. Now, from the pictorial representation, it is very obvious that in case of interstitial, the size of the parent atom and the size of the interstitial atom or the small element you're taking should have a difference. So the atomic radii is varying much. This is very large in size, this is very small in size. Whereas in this case, both of the elements are having comparable size. Clear? Okay. So for with this, we have completed the alloy interstitial compound. So thank you for your time. Okay. Next, we'll see the important coordination compound important D block element in the next class. Thank you.